So today we're happy to have Costis Papageorgakis visiting us from both Rutgers and Queen Mary in the UK. And he's going to tell us about Instanton-soliton loops and 5D maximal super mills. And tonight we'll be taking him out to dinner, leaving here around 7. So just let me know if you're interested.
Okay, thank you very much. So it's great for the opportunity to speak here. Thank you for the invitation. So as Andy just said, the title of my talk is Instanton-soliton loops and 5D young mills. Maybe a slightly better title would have been revisiting the contributions of solitons to the amplitudes. Since I don't know how much of this Instanton-soliton calculation I'll be able to cover. This is work which has been going on for some time with collaboration with Andy, and we'll see when it actually sees the light of day in terms of publications. Okay. So let me start with some motivation behind this work. From my own perspective, this kind of topic comes up if you look into a recent conjecture. I say recent, it's not that recent, it's 3 years old now, which was put forward by Mike Douglas and also by Neil Lambert, Max Schmidt-Sommerfeld, and myself in 2010, relating strongly coupled 5D super young mills and the 2,0 theory in 6 dimensions. And I will review for you how this kind of conjecture comes about and why these Instanton-soliton loops might be important in some aspects of this discussion. I should say that I'm dealing with the maximally supersymmetric version of young mills in this talk, so I'll have 16 supercharges. I'll write SYM out of sort of laziness and for being brief. Okay, so in order to revisit this kind of discussion here, I would like to remind you a few things about 5D young mills as a quantum theory. So let's start with some properties of 5D super young mills. 5D young mills, most importantly, is a theory which has a dimensional coupling. In particular, G young mill squared has dimension of length. As a result, this theory is weakly coupled in the IR and is strongly coupled in the UV. In fact, this theory is IR free. And we know from basic sort of QFT training that all theories with a positive, with a negative mass dimension of the coupling are power counting non-normalizable. And hence, they're not well-defined quantum theories, but if you think of them in terms of a Wilsonian sort of perspective, you can think of them as some low-energy effective actions which are valid up to some scale, above which the theory is UV completed by some other theory. Okay, so here I'll make the assumption that the UV completion of this theory is going to be a field theory. I mean, in principle, you have some other kind of stringy completion and whatever. And in that kind of discussion, you expect that you start off with 5D young mills, then you sort of start cranking up the energies, and you have some UV completion, which is a well-defined QFT. So the idea, of course, a la Wilson, is that you can reach both of these theories starting from some UV fixed point theory, which is a conformal field theory, and going down in energies. And if you make the following assumption that this RG flow from this UV fixed point preserves supersymmetry as you go down in energies, you would naively expect that the UV fixed point is going to be some 5-dimensional theory with 16 supercharges. Now, it turns out that NUM has performed a classification of superconformal field theories in various dimensions, and there is no 5-dimensional superconformal field theory with 16 supercharges. Okay. In fact, there is a superconformal field theory with 8 supercharges. However, it turns out that there is a natural candidate, in some sense, for a UV fixed point CFT, which is not a 5-dimensional theory, but a 6-dimensional theory. And the 6-dimensional theory is none other than the 2,0 theory, which is a very special theory. It's the 6 dimensions is the maximum number of dimensions in which you can have an interacting CFT with 16 supercharges. And this kind of relationship between this UV fixed point theory and 5D super Young-Mills is naturally understood in terms of our string theory intuition. So string theory tells us that the 2,0 theory is the low energy description of multiple and 5 rings in M theory. At the same time, we know that 5D Young-Mills is the low energy theory describing multiple D4 branes in M theory, in string theory type 2A, and then the two are related just by compactification on a circle. So you would expect naturally that in the same way, the two sort of low energy limits can also be related by compactification on a circle. Okay, so what I've said so far is nothing very deep. However, if you relate this UV fixed point theory with 5D Young-Mills in this way, you have to make an identification of parameters. And these parameters are going to be the following. So 5D Young-Mills, we just said, has a dimension for coupling, which has dimensions of length. At the same time, the 2,0 theory is a theory without parameters, dimensionful or dimensionless. However, it does acquire a parameter once you put it on a circle. So when you put it on S1 of radius r, there is a natural scale which appears. And in order for this identification that I just discussed to make sense, you relate by dimensional analysis these two scales. This can be made more concrete by comparing the superalgebras of these two theories. But immediately, just by making this identification, you have that there are 3 field theories at play here. And we'll see how these field theories are related, starting from the 2,0 theory and going down 5D Young-Mills, and then starting from 5D Young-Mills and going up in energy scales to go back to the 2,0 theory. So
that was too fast for me. What do you want to do?
Say again?
You speak so fast, so
oh, I'm sorry.
say
Yeah.
again to the last statement.
Okay, so the statement is that there is this relationship between these two theories, the 2,0 theory and the 5D Young-Mills. I'll just tell you now more analytically how they are related.
Yes.
And there's going to be 3 theories which are at play here and are related with each other, depending on what kind of energy scale you're looking at. So you start with 2,0 in 6 dimensions. Feel free to do that again. I do know that I speak fast, so. Okay, so you start from the 6-dimensional 2,0 theory. You compactify the theory in a circle. You have the 2,0 theory on S1 of radius r, keeping all KK moments.
So if I naively compactify 60 down circle, I should say G Young-Mills is inversely proportional to radius. But 60 radius.
So, in what sense is it? What do you mean? I mean, if you want to relate the radius to what the coupling that appears in front of the Young-Mills action as a parameter, what do you want to do?
I want to relate.
Yeah. So this is the relation.
Yeah. How does this come from?
Well, there's no Lagrangian description of the 2,0 theory in 6 dimensions. So this conventional intuition that I kind of dimensionally I compactify and I pick up like a factor of r in the numerator of whatever action I've got doesn't apply here. Okay, so this 2,0 theory is a theory which has a very kind of weird spectrum, right? It's got a 2 form, which is non-abelian, with self-dual connection. We don't know how to write down actions for that kind of theory. We know the superalgebra, for the abelian case at least, you can kind of, but you don't know how to extend that to the non-abelian case. So this intuition is not 100% correct that it should appear. Dimensional analysis tells you how these two things appear. Okay, so I put the theory in a circle. I have the 2,0 theory with all KK modes, and then at low energies, I reduce to 5D super Young-Mills, where I have just truncated the whole Costis spectrum. At the same time, if I start from 5D Young-Mills as a low energy effective action, and I kind of start cranking up the energy, I reach the UV completion that I was talking about, which is a well-defined quantum theory. And then, if I increase the energy even more, I arrive at the 2,0 theory in 6 dimensions that I said makes sense as a UV sort of form fixed point. So this is something that Seiberg discussed at some point in the mid-90s, and in particular, it identifies the UV completion of 5D super Young-Mills with this 2,0 theory on S1, keeping in all Kaluza-Klein modes.
So how do you do the reduction if you don't have an action? Do you look at the spectrum or what do you
So, well, you know, it's kind of, this is a discussion at the philosophical level of like, you know that the theory exists, you have this identification of parameters, and then you can try, in fact, this kind of approach is a way of defining the 2,0 theory, if you wish, by starting from the 5-dimensional theory and going up. Okay. So up to now, I mean, there's no, okay, we don't know what this is, we don't really know what this is, but there is this logical connection between these three things. And there's no contradiction. This theory is well defined at low energies, and I'm trying to see what I can tell about the 2,0 theory. So now I can tell you why this relationship becomes particularly interesting, because 5D Young-Mills has an interesting solitonic spectrum. In particular, it has a nice conserved charge, the conserved current. So the following star J is trace F which F is a conserved current in 5-dimensional theory, where the star is the 5-dimensional Hodge star. And this means that 5D Young-Mills, there are states carrying Instanton charge. So these states which carry Instanton charge are conventional solutions of the self-duality condition of the gauge field in the 4 spatial directions of 5D Young-Mills. These states are half BBS, and they also have a mass which goes like K over Gn squared, where K is the Instanton charge that I'm considering. So as far as solutions go, these are the conventional Instanton solutions that we know from 4-dimensional Young-Mills, but in this case, they are particle-like solutions in 5-dimensional theory. So they are solitonic objects of finite energy, and in order for us not to get confused, I will call them Instanton solitons. Okay. Great. So the interesting thing here comes from the following observation now, that we said that the Young-Mills coupling squared can be related to the radius of the quantification circle on which I put the 6-dimensional theory. However, the mass of these Instanton-solitons goes like K over Gn squared. This would imply that I can write this in terms of K over R, and of course this now starts looking like Kaluza-Klein momentum along the direction in which I theoretically have compactified the 2,0 theory. Now this seems to be a little bit confusing, because here I told you that 5D Young-Mills is the truncation to the 0-mode sector of this compactification on a circle. And yet you see that the non-perturbative spectrum of 5D Young-Mills seems to know about momentum along the this circle. So it seems like 5D Young-Mills actually has a way of encoding the physics of this UV completion of the theory. And in that sense, it's natural, if you wish, to investigate the possibility whether 5D Young-Mills does not require sort of auxiliary UV completion, but it has all the degrees of freedom on its own, in its own right, in order to be able to describe this stage here. And that led to the conjecture that I spoke about at the very beginning. This conjecture can be split into 2 parts. In particular, you can think of part 1, let's say part A. So 5D Young-Mills at strong coupling is the 2,0 theory. In 6 dimensions. So in that sense, you provide a definition of the 2,0 theory from the point of view of this 5-dimensional theory. But then, of course, this requires something slightly more fundamental. I told you at the beginning that this theory is supposed to be non-normalizable, so it's not a well-defined quantum field theory. So in that way, how does it make sense for me to go at high energies, and how does it make sense to, consider strongly coupled 5D Young-Mills? So there's a part 2 of this conjecture, which says that 5D Young-Mills is a well-defined quantum field theory. Any questions so far about this discussion?
What's the effective energy scale for the?
Yeah, so it's interesting. I mean, there is one energy scale which seems to be natural here, and would be this Kaluza-Klein scale, 1 over GM squared. But there doesn't seem to be any other sort of natural scale in the resistance problem. So somehow, there's no. Usually, you say that there is some scale, and I kind of decouple these kind of massive degrees of freedom. When G Mills is small, these things are very heavy, and somehow you don't see them. But
What does a well-defined quantum field theory mean? What do you
it means
mean?
that you don't have UV divergences. It's a normalizable theory in some sense.
Well,
So that's what I'm
you
gonna-
mean with well-defined. Okay.
Yeah. So I'll come to that now. Okay. So as far as part A goes, if you just take this idea and run with it, can you sort of get in mileage? And there's been some interesting work over the last 1 year where people have applied the techniques of supersymmetric localization of Peston for 5D Young Mills and some S5 or other sort of 5-dimensional compact manifolds. And they do seem to be able to reproduce the full BPS sector of the 2,0 theory. So I should say that the BPS sector of 2,0 and 6D agrees with the BPS sector of 5D super young Mills. From the point of view of the 2,0 theory, of course, you don't have a Lagrangian. How do I know exactly what the spectrum is? I don't even know what these non-abelian two forms are. But you can use ADS-CFT to work at large n, and you can calculate a superconformal index on ADS7 times S4. You count the spectrum of supergravitons, and you can make a comparison, and you get the answer to come out the same. So the BPS spectrum of the two theories seems to agree. Of course, you can tell me that this is not enough for the two theories to be the same. There's also a non-BPS sector. Or even if the BPS sector agrees, what about the dynamics of the two theories? It's not clear that this is something that you can answer in this way. But what I would like to focus on today is this part B and try and discuss how this 5-dimensional theory could be a well-defined quantum field theory. You look?
Yeah.
Yes.
If that means renormalizable theory, so why did you write down? And
Yeah, good, very good. That's the whole point. So I should say that conventionally, this thing is a non-normalizable theory.
Since this theory is strongly coupled, normally we expect there should be lambda code. So the scale is lambda code.
So we'll see. So I'll come to what the expectation is and what has been observed for this part of this idea. So first of all, this is a maximally supersymmetric theory, and maximally supersymmetric theories don't exhibit UV divergences perturbatively up to some high loop order. Okay. In particular, when these conjectures were made, the first UV divergence of 5D angles hadn't been seen yet, because this theory is protected up to 5 loops from supersymmetry. So no one had been crazy enough to do this kind of calculation. However, McDougall managed to convince Byrne, Dixon, and all these people who do this thing for a living, and last year they did a calculation at 6 loops, where they would try to evaluate the coefficient of a particular dimension 10 of the ray counterterm that you can have in 5D Young Mills, and see whether there's any other reason for which the coefficient of that counterterm is 0. And they did the calculation numerically, and they found that the coefficient is not 0. So there's no reason beyond supersymmetry to expect that these high-dimensional counterterms that you can add to your 5D Lagrangian are not present. Okay? So it would seem that perturbatively 5D super Young Mills is divergent. So the next question you'll ask me is,
sorry, maybe this is a stupid technical question
Sure.
before you go. So BPS, how many supercharges?
16, so
16.
we're also always talking about 16.
And how many for fractions?
I think
has it
half
been
and
done?
quarter
Half
has
and
been
quarter?
done, yeah.
Okay.
Okay, great. So this is where what we're doing with Andy comes in. And the idea of our work is that what if the non-perturbative spectrum of 5 Young-Mills, which is in fact very, very important in making this BPS agreement work, is also responsible for some kind of perturbative, for the cancellation of the perturbative divergences that you see in this kind of idea. So immediately you tell me, what are you talking about? Soliton contributions to perturbative amplitudes are exponentially suppressed. Okay, this is the law that goes around. Well, so this is the thing that we also try to investigate and see, in what sense these things are exponentially suppressed, etc., etc. So the first thing that you encounter when you ask yourself that question is suppressed in what? And conventionally you say that the suppression is some factor which was like 1 over g squared, where g squared is the coupling. Of course, this works very well when the coupling is dimensionless. But in this 5-dimensional case, when the coupling is dimension 4, this exponent is not dimensionless, so you have to make it dimensionless somehow. Well, it turns out that in Soliton physics there exists a natural dimensionless ratio. And this ratio is given by the Compton wavelength of the soliton over its size. I remind you, the Compton wavelength is just 1 over the mass of the soliton. So, okay, the idea is what, for example, for the monopole in 4D, conventional 12th quality monopole, the Compton wavelength is 1 over the mass, and this is g squared over w. The size of the monopole goes like 1 over w. So the ratio of Compton over S comes out to be g squared. So I want to claim that this exponential suppression is going to be something like size over Compton wavelength. So this is a dimensional analysis kind of argument. Okay, the question is, can I apply this to the case of my 5-dimensional theory? Is this the scale in which these Instanton-soliton contributions are suppressed? Well, in 5 dimensions, the Compton wavelength is again 1 over the mass. We calculated what the mass is there. It's g(m) squared over k, which let's choose Instanton-solitons of charge 1. The size, however, of the Instanton-solitons in this case is a modulus of the theory. So I remind you that the Instanton profile looks something like this. And okay, so sigma mu is some antisymmetrized combination of sigma matrices. These nus run from 1 to 4 in this case, and I have 8 degrees of freedom associated with moduli. I have 4 translations associated with moving the Instanton in R4. I have a size rho, and I also have 3 degrees of freedom associated with these global gauge transformations, which live in your gauge group. For SU2, that's right. For SU2, there's 3. For generic gauge groups, of course, it's more. Now, this modulus is what appears here. And as you can see, if I take this ratio of size over the Compton wavelength, this gives me rho over g(m) squared. And as far as these Instanton solutions go, this rho can be arbitrary. In fact, there is no preferred size for these Instanton solutions. So it seems like there exist sizes which are of order g(m) squared, for which this contribution, in fact, would not be suppressed according to this naive argument. And this contribution could be order 1. So immediately you ask yourself, okay, so what's happening here? Are these contributions neglected in the conventional arguments? Should you be taking them into account? Yes, no. And also, how do you make this thing slightly more quantitative instead of just like a dimensional analysis kind of argument? You would have expected that these arguments must have been done at some point in the 70s, where soliton physics were quite popular and people were inventing these kinds of approaches. But we've searched high and low, and in fact we haven't found any kind of treatment of this stuff in the literature. So,
But it does seem quite similar to the usual sort of quotation of the infrared catastrophe for instantons, right? That there, okay, you start with a dimensionless coupling, but the stupid thing does run, and you go to strong coupling, and then you have these point-like instantons that you don't know how to make sense
yeah,
of.
but for instantons, somehow, I don't know, seeing this suppression is slightly more intuitive. You know, you write down a path integral, you integrate over all Euclideanized sort of, dimensions, and then you get an e to the minus 1 over g squared. Somehow, if you compare these things, the perturbative contributions is suppressed by this factor. In this case, you have solitons, so you have finite energy configurations, and things are not as simple, at least.
No, I'm saying maybe it's the other way around, that even in the good QCD case,
Right, yeah.
I don't know how to deal with
good.
the instantons there, right?
Good.
Point-like.
So this is the essentially what we've been trying to do. We've been trying to come up with a formalism that tries to account for the solvent contributions in perturbative amplitudes. Try to apply it first for the conventional case of monopoles where you expect exponential suppression to come out like this, and then see if you can extend that to the case of Instanton-solitons in this 5-dimensional physics. So in order to do that, let me begin by considering some kind of d-dimensional quantum field theory. The only requirement I'm going to make is that I have some gauge interactions, and let's consider a particular process in this theory, in particular that of the Clone self-energy. So I would like to try and evaluate the contribution of solitonic states, or solitons running in loops, if you wish, for this problem of this Clone self-energy. Now, conventionally you say, okay, I use Feynman diagrams and I calculate what the contribution is, but I don't know how to do Feynman diagrams for solitons. So instead what I'm going to do is I'm going to perform a unitarity cut and consider this as having a complete set of intermediate states, and I'll use the optical theorem to relate 2 times the imaginary part of this amplitude to the sum over all intermediate multiparticle states where this f here. So here I sum over all multiparticle states. This is the multiparticle phase space, and then this f can be any intermediate state I can have here. Now the question is, what can these be? Conventionally you'd say it's just perturbative particles that are exchanged between these gluons, etc. However, the only requirement that I have to satisfy here is that I remain in the zero topological sector at the beginning and the end of my process. In the middle, I can have soliton states that get exchanged as long as the total topological charge is 0. So this is
the optical theorem. Do you assume the theory is already realizable?
good. Yeah. So in all of this approach, you begin by assuming. I mean, in the same way that you look at divergences in any theory, you start by assuming the theory is fine, and then you run into a problem. So we'll do the same thing. We'll start by assuming that the theory is fine, and then see if you get the divergence. Good. So I'm going to focus only on one process that can appear in this set of intermediate states, which involves a soliton of momentum p and an anti-soliton of momentum p prime. So this is what my f is going to be here. And the question is, can these contributions actually appear in this kind of calculation, and how do these contributions compare to the conventional perturbative contributions? So in order to do this, I would like to relate this amplitude in the usual way to a matrix element. So here there is some factors of phi, some delta functions, and when the amplitude of L goes to left, let me write prime can be related matrix element where here I've just expanded the S matrix, or the interacting part of the S matrix, and HI is the interacting Hamiltonian. I've put the dots here since I'm interested in looking at the behavior of these contributions to leading order, and all these kinds of diagrams here are going to be subleading in this expansion. So in the theory that I want to consider with gauge interactions, of course depends on what kind of theory you're thinking about, but I would like to have a term which E-1, which involves the gauge current for this non-abelian gauge field multiplied by mu. Therefore, the term that I'm interested in here is going to be something that looks like D prime bar trace of J mu mu. Oh. Okay, so I claim that doing calculation for this matrix element will give me information about whether these soliton are contributing or not to this perturbative diagram and how these compare to the perturbative calculation. Now, the difficulty with calculating this kind of matrix element, of course, is that I don't know how to understand this soliton and the soliton bound state. I don't know how to write down, I don't know what kind of mode expansion this thing is. But what I can do is use crossing symmetry and using crossing symmetry, I can relate it to the following matrix element. Now note that this crossing symmetry has done something non-trivial. It's taken me from the zero topological sector to a topological sector of charge 1. Okay, I've taken this anti-soliton, which was an outgoing state, and I've made it an incoming soliton state. I'm also going to get rid of this gluon here by formally writing the mode expansion for this gauge field in this one soliton background, in which case I'll reduce this to trace mu. There's going to be some polarization vector. There's also going to be some function, which is the analog of the plane wave that we have when we do mode expansion around the perturbative vacuum. There's going to be some function of, well, it's going to depend on the moduli of my soliton, which I'm going to note by u. And therefore, I've reduced the problem of investigating the contributions of these solitons, the perturbative amplitudes, to evaluating this one-point function in the background of the soliton. Okay? This is what is called a soliton form factor. And it turns out that, I mean, you'll ask me why did I do this crossing symmetry? Do I win something by going to this one soliton background? And the answer is yes, because there is an approximation in which I can understand what these states are. I can write them down, and in particular, I can do this calculation. Now, any questions up to this point? So the approximation that I'm going to do is the so-called Manton or moduli space approximation. In particular, I'm going to be interested in the semi-classical expansion of the various fields that appear here around the classical soliton solution. So any field phi has an expansion in terms of a classical piece, which depends on position variables and also on the moduli, which I denote by u. And then there is also a fluctuation around this classical background. Conventionally, these fluctuations are sort of massive oscillators. The way to use this expansion and go properly to the quantum theory is not by including the zero modes here. There are zero modes associated with this moduli, but to promote these moduli to functions of time, and here just have massive oscillators. Now, in the Manton approximation, or the moduli space approximation, you ignore these fluctuations, the quantum fluctuations around the soliton background. I promote these things to functions of time, and I also go to a non-relativistic limit where I take that the first derivatives of these moduli are small. That means, in a sense, that these moduli or these solitons are very slowly moving. Okay, great. So in that limit, it turns out that the whatever classical action you have reduces to, so the theory, whatever your action, the dynamics, the whole dynamics reduced to, from the full quantum dynamics reduced to dynamics only for the zero modes. So classically, you reduce to a free particle mechanics on moduli space. So you have some action type where the ordinates now are your moduli V, and this is the metric on the moduli space. And also you have that the sort of full quantum dynamics reduce to quantum mechanics on this moduli space as a result.
Costis,
Yes?
does this place any restrictions on rho or no?
So good. No, it does not. And I mean, now I'm having a very general discussion here, but because the theory that we're considering is maximally, in fact, this is a generic sort of property of all these moduli spaces. So the targets, which correspond to the moduli space metric, are all hyperkähler manifolds. And as a result, these things are not normalizable in the full quantum theory, which means that you don't have, like, you know, the lifting of some of these directions, which would force you to pick a particular size for this soliton modulus rho. So this is a bit of a puzzle, you know. How can you have? I mean, usually we're allowed to have non-compact directions associated with motion in the moduli space, but all the other directions are usually compact. This theory seems to have a non-compact modulus for this size. Okay, so we reduce to a quantum mechanics in the moduli space, and in particular, the one-point function that I wish to evaluate here in the quantum mechanical approximation is going to reduce to an expectation value for this function in the middle, evaluated in the soliton background. So how can I express this in terms of this quantum mechanical setup?
And from where do you read off the metric on the moduli space?
Yeah, good. So you have to evaluate it. You have to calculate it. So you fix a theory. You have a soliton solution. I'll give some examples towards the end. For monopole, for example, you know that monopole in SU2 theory has moduli space are 3 times S1, corresponding to 3 translations, and there is one compact direction, the conjugate momentum of which corresponds to electric charge, which is quantized, and dynamo charge, it's a electric charge. For Instanton-solitons, the moduli space metric is different, and it becomes sort of increasingly harder if you increase the rank of the gauge group to find what these metrics are. So I'll break down, in the end, I write down what I want to calculate, and I'll break down the components that you need to have knowledge of in order for you to be able to do the calculation.
I'm also a little bit confused,
Yeah.
Just what you were saying.
Yeah.
How much are you biting your own tail? That you say, oh, I have a well-defined theory.
Yes.
In order to check whether I do, I will do this computation.
Yeah.
But to do so, I need to, for example, know the moduli space metric, which I compute by using.
But what's the only
Well,
thing
the
that I
moduli
use?
space metric presumably will receive quantum
No, it
corrections.
doesn't. It doesn't, because the moduli space is hyperkähler. It doesn't receive any correction.
The metric does not.
Yeah.
And why do you know this?
I think there are some normalization theorems from the 70s that tell you that sigma models with in well-defined theories you'll tell me. But this moduli space, this theory that you receive by looking at the low energy modes is a well-defined theory.
The name of the game is what I was saying before.
Yeah.
Assume the full theory is well defined and see if you arrive at it.
That's how you usually get these problems, though. You assume that the theory is well defined, you calculate something, you find a divergence, you say my theory is not well defined. We're doing exactly the same.
Okay, right. And then your nonlinear sigma model has enough supersymmetry.
That's right.
Okay, cool. Okay, got it. Mm-hmm.
Any other questions, comments? Okay. So what I'm going to do now is I'm just going to write this quantity here in terms of the expectation value in this quantum mechanics. I should also say that since I've expanded all my field in terms of a classical piece and some kind of fluctuation that I ignore, this J mu that I have over there is going to be just replaced by the classical gauge current evaluated in the soliton background. This classical gauge current in principle has some dependence on the positions in space-time, and also the moduli of your soliton U. And hence, the expectation value that I'm trying to calculate is going to look as follows. I'm also going to perform a translation and go to a limit where the incoming soliton is going to be at its center of mass frame, so it's going to have zero momentum. In which case, I know the classical solution around which I'm expanding is the static monopole solution, or the static soliton solution. If I want to have something which moves, I can perform always a boost and go to some moving frame. Okay, so let me call this P, trace, G mu, L, psi hat of L, some function 0. So this thing you can now rewrite in terms of the following. It's a little d-dimensional integral over the moduli space coordinates U. Little d denotes the dimension of the moduli space. I have to sandwich these functions here inside the wave functions in the moduli space. So I have J mu classical, epsilon mu, function of L, psi L, psi 0. And I also have to pick a volume factor associated with the volume of the moduli space. And this is it. So the whole discussion of how you can investigate the contributions of solitons to perturbative amplitudes boils down to evaluating this quantity. So the thing, of course, that we're interested in, let me recap on what you need in order to do this calculation. First of all, as we just said, you need to have knowledge of the moduli space of the theory. You also need to have knowledge of the wave functions of the moduli space. I also need to know this classical piece, so J mu classical, and I also need to know what this, let's say, mode expansion of a mu is in the soliton background. So, of course, once I have knowledge of all these four ingredients, I still need to perform the d-dimensional integral of the whole moduli space, and I claim that this is going to give you an answer, which is going to tell you what this form factor is, and then after performing crossing symmetry, I'll be able to stick that into the to my original calculation and compare with perturbative calculations. So this is all very nice in theory. Now let's focus on, in the last 15 minutes, on a particular example to see how it works in practice. Any questions? Comments? Okay, so let's make this a bit more concrete and look at example 1. It's going to be polyatomic monopoles. In SU2 Dimensionless Higgs theory. So, what do we need to know in that case? We need to know the moduli space. As I mentioned briefly, the moduli space in this case is R3 times S1. And this corresponds to translation in the three spatial directions. This is a four-dimensional model. So there's three translations, giving this factor of R3. There is also a modulus chi associated with the conjugate momentum to this S1. Since this is a compact, it's a circle, this conjugate momentum is quantized, and this quantized number corresponds to the electric charge carried by your monopole state, in which case it becomes a time. Next thing, we want the wave functions. Well, you can even write down the metric explicitly in this case. I don't know if this is useful. This metrically are 3 times S1 with some coefficients. Next thing that you need is the wave functions in the modular space. So the wave functions are parameterized by this conjugate momenta to x0, I call them p, and the quantized integer conjugate with this guy, and is a function of x0 and chi. And I can write these things explicitly in this four-dimensional model as a plane wave factor, and also a corresponding thing for this S1 direction. Okay, it's nice and simple. I also need the value for J-mu classical. Well, you can evaluate that easily. It's given by a commutator. So this is a non-supersymmetric theory, by the way. Fully bosonic. I can evaluate this commutator when all the fields assume the classical values. I'll get an answer. And the final ingredient that you need before you do the integration of a multiplex space is the smooth expansion of a mu in the Soliton background. So we need this psi of L. This is the piece that we haven't calculated yet. So we haven't been able to finish the calculation explicitly. But I can give you a qualitative argument why doing this integral is going to give an answer which is exponentially suppressed. Okay, so this is something that we're in progress of doing. But there is as I said, a nice qualitative reasoning why this approach is going to give you an exponentially suppressed answer. So we want to calculate this trace of E n, where you've sandwiched trace of J-mu classical, L, epsilon mu, L, inside the monopole with zero momentum and zero electric charge. This is the usual sort of topological solution.
One-to-many traces.
One-to-many? Yes. So, an interesting observation is that if you write down the form of the classical profiles for these fields here, you get that these profiles phi are exponentially suppressed at large x0.
I missed it. What is phi?
Phi? Phi is the scalar, it's just a Higgs
Oh,
field
just a scalar.
in this topological form. So there's a phi, there's also some associated gauge field. The solutions are given by some in the BPS limit, by some complicated expression, involving some hyperbolic trigonometric functions, etc., etc. The part of the solutions that I want to use is that if you look at the limit where x0 goes to infinity, they have an exponential fall-off. And in fact, the fact that these things have an exponential fall-off feeds into this current having exponential fall-off itself. As a result, this function here has an exponential fall-off at x0 going to infinity. And let me call this function f of, let's say, 0 and chi. And essentially, the integral that I want to perform here is I want to integrate over the 3 x0s, x chi, x naught, and chi. Now, yeah, so the wave functions, that's right. So let me pull out the wave function piece. Okay, so I want to perform an integral of this type. This is the integral over this S1 factor, and it is a compact integral. It's not going to give me any kind of information about how this thing is exponentially suppressed or not. In fact, what this should give me is just a conservation of electric charge condition between the incoming guy and the outgoing guy. In particular, this should just pick out the charge of this mediating gluon. Okay, should be plus minus 1. This is a W boson. So let me not care about this, broadly speaking. The remaining piece of the calculation that I have to do is simply a Fourier transform of this function f. Sorry. And I told you that this function here is exponentially suppressed at large chi naught. It's also a function which is smooth all over the sum 3. And these functions, the functions of these properties have a particular name. These are called Schwartz functions. Schwartz functions, they're smooth functions with an exponential O. The interesting thing about these Schwartz functions is that the Fourier transform is an automorphism of these functions. What this means in practice is that the Fourier transform of a Schwartz function is again a Schwartz function, which means that it's again exponentially suppressed. But it's not exponentially suppressed in this variable, it's exponentially suppressed in the dual variable. Therefore, this integral is going to be proportional to e to the, let's say, p times some scale, and W, broadly speaking, it's going to be exponentially suppressed at large e. And how, you ask me, does this have anything to do with exponential suppression? Well, in the gauge coupling, well, if you then use crossing symmetry, so use crossing symmetry, and you go back to the process where you look at the reproduction of soliton and soliton, reproduction of solitons and solitons, you end up having that this P here is proportional to the incoming momentum, which I've raised, of the incoming gluon. This thing itself has to be bounded by twice the monopole mass, because if you have an incoming gluon of some energy, the energy has to be at least twice the mass of the monopoles to produce these pairs. And if you stick that in here, you get that this factor goes like minus 2m over w, n was in w over g squared, so you get 2 over g squared. And that's the exponential suppression that we expected from the very beginning by this dimensional analysis argument. So this is the, let's say, qualitative argument about why these contributions are exponentially suppressed. We still need to, I mean, I'm suppressing many, many details in this discussion. There are issues of like how you choose gauge, etc., and this calculating this component here of this calculation should give an answer where all the details come out right. So having discussed this, let me just sketch what happens when you try to apply this to the case of Instanton-solitons in 5 dimensions. Okay, so finish, let's look at example 2. Which is going to be Instanton-solitons in 5D maximally symmetric monomills. And for Instanton-solitons, we said, I think we need a little bit more specific. I'll choose the gauge group to be SU2, because that's the only thing that we can actually do. Calculating the moduli space for higher rank gauge groups is very, very tricky. The integrals are also very tricky. So moduli space is R4 times R plus times S3 mod Z2. You might know this as just R4 times R4 mod Z2. This thing is associated once again with translations along the 4 spatial directions. This thing is associated with the non-compact size of the Instanton row. Then this thing is associated with these SU2 global gauge transformations, because I've got a thing with adjoint fields. These transformations have to be modded out by the center of the gauge group, which is SU2 mod Z2. SU2 is isomorphic to S3, so hence the S3 mod Z2 factor. Okay, so this is the moduli space. You need to also know the wave function on the moduli space. This is a bit of a nightmare, because instead of having in the Manton approximation just quantum mechanics on the moduli space, you have a supersymmetric quantum mechanics on the moduli space. if you want to quantize that thing in order to take into account properly of the supersymmetry in the moduli space, you have to promote your wave functions to spinor wave functions. The reason for that is that the fermion collective coordinates get promoted to gamma matrices upon canonical quantization. These have a natural action in spinors. It's a rather technical subject. You can calculate the wave function explicitly. We have done this. We know what this piece is. You also need to calculate J mu classical. Conventionally, this would be something, again, like this commutator plus fermions evaluated at the classical value. But of course, for an instanton profile, there's no non-trivial expressions for the scalars and the fermions. These things are automatically 0. So naively, you'd say that, oh, my gauge current is 0, the form factor is 0 automatically. However, since we're thinking about the maximally supersymmetric theory, there are fermion zero modes that you can turn on. These fermion zero modes generate expressions for these scalar and fermionic fields. In fact, this J mu classical turns out to have a nice expression in terms of the zero mode, the bosonic zero modes on the n multiplying fermionic collective coordinates. It's a nice commutator of bosonic zero modes on this moduli space. We know what this piece is as well. And once again, the thing that we do not know is the equivalent of the expansion, the mode expansion of the gluon in this instanton profile. Once again, though, we can try and use this Schwartz argument to have some kind of expectation of what the answer is going to be. And in contrast to what happened for the monopole case, where these phis, the profile for these functions was exponentially suppressed at the large x0, instanton profiles are not exponentially suppressed. They fall off with a power law at large x0. So in that sense, they're not going to be Schwartz functions. And the Fourier transform, because the integral that you have to perform is going to be a generalized version of this. You can have a d4x0, an integration of a rho, and also an integration over the gauge orientation, these two gauge orientations. But there still is a piece of these wave functions which is has a plane wave factor. You still have to perform a Fourier transform, and the answer is not going to be exponentially suppressed in the momentum. So this is something that you can see already. Now, the shocking thing about this observation is that initially dimensional analysis would tell you that only the small size Instanton-solitons are the ones that are responsible, if at all, for these contributions, which could, in a fantasy, cancel the perturbative UV divergences. But here, this calculation tells you that it's just the form of these Instanton solutions that tells you that there's going to be no exponential suppression if you follow this calculation. So with that, I'll just close by saying that we need to have some kind of, this is a rough argument that doesn't necessarily let you calculate anything explicitly. You tell me that in order for me to, make this thing concrete, I have to calculate the contributions coming from these guys, do the calculation that, would be contributing at the same loop of the 6th loop perturbative divergence in 5 Young Mills, find the same answer with the opposite sign so that these two things cancel, and then I have to do that an infinite number of times for each divergence that I get from the perturbative calculation. Of course, I can't do that. I don't know how to do that in principle, that's the fantasy. But it kind of tells you that this idea that this 5D Young Mills theory is somehow less trivial than originally thought, might have some mileage in it. And in particular, it kind of brings back into the fore this kind of question about whether these Salton contributions, which naively you say are exponentially suppressed, should be included in other theories that you can do this calculation. And just as a final word, I should say that there is a check that you might be able to perform for this kind of calculation. So Mike Douglas was investigating the compactification of 5D Young Mills on a circle. So he looks at the perturbative amplitudes and what happens to them when, the 5-dimensional theory, what happens to them when you compactify on NS1, but keep the KK modes and not truncate them. So the question was, what happens to these KK modes under S-duality? And some people say that imposing S-duality for these amplitudes is equivalent to saying that 5D Young Mills is the 2,0 theory and you shouldn't impose it and it should come out, etc. But if you do that, you find that these amplitudes are not S-duality invariant. So there's a piece which is missing. And these kinds of contributions from these Instanton-solitons could be both diverging but also finite. So it could be that there is a finite piece which you can calculate already at one loop which might complete this non-S-duality invariant perturbative calculation into an S-duality invariant answer. This might be a way to kind of go ahead with this. So thank you for your attention.
Questions?
What's that?
As the resident mathematician, I have to quibble
Yes.
that you can't conclude that the Fourier transform of the Schwartz function
Is that right?
exponentially decays. All
Okay.
you can say is that it decays faster than any power.
Okay.
So it might go like e to the
That's
minus 10th root of p or something like that.
Correct.
And perhaps more important is that it's the smoothness of the original
That's right.
that matters.
Yeah, exactly. So the gate, that's a very important point.
Falling off,
Yes.
like the
Yeah.
power in x doesn't have anything to do with whether it falls off of power in p. It's the smoothness in that.
Okay, yes,
Yeah.
yes. So as far as I understand, Schwartz functions have to be smooth and have to be also falling faster than any power, and then you can
Right.
say that there is a
And the Fourier transform.
Exactly, exactly. So yeah, that's a very important point. I said that there is some subtlety with
But
choosing
there are all
gauges.
sorts of theorems like that,
Right.
that are less,
Restrictive.
right, the smoothness on one side corresponds to decay on the other.
Okay, great. So I would love to actually talk to you about this.
No questions? If not, let's thank Costis again.